So let me tell you what our goal today is. We're going to be doing a new section, 13.4. It's motion in space in 3D. And here are the four main topics. The first one is if you have an object moving in space, right? So there is space curve, vector function, its various names, this green curve. At any given point t, we can find what's called the velocity vector, which is essentially just the first derivative. We can find the acceleration vector, which is essentially the second derivative, just like in Calc 2, right? You take a function, a position function, if you differentiate it, you get the velocity function. If you differentiate that, you get the acceleration function. So it's very similar to what you would have done in Calc 2. And then we've got this guy here, which is the speed. And the speed is a scalar. And what that means is it's a number, or at least it's a function of t, like t squared plus t. These two things are vectors. This is a scalar. So you might say, well, we very often mistake velocity and speed. We interchange them as if they're identical. And although they tell similar things, they're not identical. In 3D, a velocity is a vector. It's that pen. The speed is the speed, like I'm traveling 40 miles an hour in this direction, or I'm traveling 400 miles an hour if I was a jet in this direction. So there is a difference between them. If you look at how you calculate them, of course, isn't the speed just the magnitude of the velocity? So if you found the velocity vector already, then you only need to do the magnitude and you are done. Now, you could find these things at a given value of t, like at t equals 10. But as far as I can tell, it seems that we want to get them as functions of t. So whenever you imagine an object traveling in 3D space, and you choose a point, call it t, the curve will be there, and the velocity vector would be that. That's the direction you shoot off to your death in, right? The analogy with the roller coaster. And the acceleration vector basically has an x, y, and z component. And what that tells us is how this vector is going to be changing in the next second. Maybe its x will become a bit faster. Maybe its y direction will become a bit slower. Maybe the z direction will stay constant. So at any given point in time, won't this vector change as you travel along the curve? And the acceleration vector is an indication of how that change is going to happen. We go back to the 2D world, isn't acceleration a measure of the change in velocity with time? Right. That's basically what it is, the rate of change of velocity. So, three formula to remember. Velocity is the first derivative, acceleration is the second derivative, and the speed is the size, the magnitude of the velocity vector. And we are going to have to deal with them mostly in terms of t. And so we're going to use quite a few of the tricks that we might have met, especially down here at the last one, to come up with that. But in general, the questions do tend to be a lot easier. So the first 5 questions are going to be on this topic. Here is our first, here is our first question. It's similar to question 1. This one has just got polynomials in it. So it's t squared plus t squared take away t, and t cubed. And we're being asked to find velocity, acceleration, and magnitude of the velocity, which is the speed. So let's get velocity first. Well, it's the first derivative. And that's the easy one, right? Differentiate 2t plus 1. Differentiate 2t take away 1. Differentiate 3t squared. Everybody's happy. Now, if you want to, that's it. That's velocity finished. If you want to get acceleration, you can find the second derivative of position function. Wow, this thing's got a lot of names. It's position function, right, this guy up here, position function, space curve, vector function. And I think there's a fourth name I can't remember right now. It's the same guy, right? Just different names. Excuse me. If you differentiate this guy, you get 2. You differentiate this guy, you get 2. And you differentiate this guy, you get 6t. And unless these functions here are ugly, you know, you might have to do a t sine t, which would be what, a product rule. Or you might have to do e to the 5t squared, which would be a chain rule. Or one of these things up here might be a fraction, like t over t squared plus 1, in which case you're going to use the quotient rule, right? Most of the time, you know, we know how to differentiate, so it won't be too bad, I would hope. Now you need to get the speed. And that's the last thing I ask you for. And the speed is the magnitude of the velocity vector. So if you imagine this pen being the velocity vector, the speed is the length of it. And if that length was 100, that would represent you're going this direction at 100 miles an hour. Right, so at least speed kind of makes sense if something's moving, right? Because couldn't it be I'm going in that direction at 4 miles an hour or 40,000 miles an hour, right? That's the difference between, you know, a rocket and a person, right? Same direction, but different speeds.
So that speed is just the velocity vector going in that particular direction?
Yes.
Okay.
And it's a magnitude of the velocity vector going in that particular direction, right? Now, we know how to get magnitudes of vectors, even ones that have t's in them. It's this guy squared plus this guy squared, finally plus 3t squared. So far, so good. Velocity, first derivative, acceleration, second derivative, and the speed is this guy. Now we have to employ what I call style points, which basically means make the thing look pretty. So do not leave it like that. That would be considered bad form. I'm going to cut some corners here. If you FOIL this out, you'll get 4t squared plus 4t add 1. If you FOIL this guy out, you'll get 4t squared minus 4t plus 1. And if you do this guy, you'll get 9t to the 4. Now what I'm going to do now is collect like terms and put them in order highest first. So that's that guy. This fella gets killed off by this guy. The next power is adding those two guys together. As I said, these kill each other off, and then you finish with that.
Hey, Professor, I have just a quick question. This is something I know I should know, but when the 3t squared that's in the parentheses that's being squared, is the squared, are the two squares multiplying or are they adding?
They're multiplying. Well, they are multiplying. Essentially what you're doing is you're taking this guy and you're multiplying it by himself, right? That's what the squared means. Now the numbers are 9. What a lot of people sometimes kind of confuses that when you multiply 2 powers of t together, you add their powers. So if this was t cubed and this was t cubed, I would get 3 plus 3, I would get t to the 6. I know you're adding powers, but essentially you're multiplying things, right? Does that help?
That helped, thank you.
Okay. Now, typically, if you see 3 things inside a square root, right, you should be thinking, at least on Monday's work, shouldn't you be thinking of perfect squares? And sometimes the thing will be a perfect square, but not this time. And basically, I can tell you that the if it was going to be a perfect square, wouldn't it have to be 3t squared plus the square root of 2? And if you FOIL that out, it doesn't work. So that's basically finished. Now, I'm going to show you, hopefully show you, what you might have to do when you do your answers in WebAssign. And this might lead on to something you were saying earlier, Calvin, about you know you're right, but it wasn't taking it. Right. You click on this guy. The velocity, well, I have it here, is 2t plus 1. You have to go down to vectors and you have to hit that guy. And you put in, I'll use this guy here. You put in the 2t plus 1, comma, 2t take away 1, comma, and what is the other guy? 3t squared. Now if I copy, now if I put the less than symbol, and let's just copy this. Well, let's put in the answer. The answer was 2, 2, and 6t. So 2, comma, 2, comma, and 6t, and I finish with that. Would you agree it looks like I've written it out in the correct format, right? It's got the little funny brackets. WebAssign will say yes to this one and say no to that one. You must use that symbol there when you do vectors, right? Not the less than or greater than symbol, because it is, for all intents and purposes, doesn't that look like a greater than and less than symbol, but it has to be done in this vector bracket format. Okay, and this answer, well, no, I'm not changing it now, but, and the last one is a little bit easier. You type in the square root, and then you just put in 9t to the 4 plus 8t squared and plus 2. So that guy there, let's get rid of the ones that don't work. Hit the vector button, put that one in. There you go. That's how it should look when you're doing your homework for this question. Are we good? I don't know if that was one of your issues, Calvin. Did you write it down with the wrong buttons, maybe?
Well, one of the questions that I remember having issues with was like where the questions in 13.1 where you had to put in the X, Y, and Z. Just a couple of those, just putting in the values, and I thought that they wanted them put in like X equals such, Y equals such, Z equals such.
Okay. And sometimes when they do that, they don't want you to put the X equals part in. Sometimes, like let's say it, let's just for argument's sake say it was this, right?
Yeah.
Sometimes they just want you to do this.
Okay.
And sometimes they just want you to do this. But no brackets around it.
Yeah.
So it's the idiosyncrasies of what WebAssign will and will not accept. Okay, that's our first guy in town, right? Are we comfortable that if I give you a space curve R of t, that you know the math to get the velocity, the acceleration, and finally the speed? And the style points, if there are going to be any, will probably end up in the speeds, right? Because when you differentiate these, there's not much you can do to them. So the next one is a version of question 2, and it's the same question: velocity, acceleration, and speed. In fact, the first, check it. Yeah, the first 5 questions are essentially asking the same thing. Although once you've done enough questions, you kind of see things that you think, I've seen this kind of situation before. Do you recognize that one as being a helix, one of those circle spirally guys of some kind? Whenever I see cosines and sines floating about, there's going to be a very good chance that when we come to do the speed part, that we'll be able to simplify it in some way. So let's get velocity first. It's just the first derivative. And so differentiate a cosine, you get a negative sign. The guy in the middle is 6, and the guy at the end is 2 cosine t's. So that's that done. Acceleration is just second derivative. If you differentiate -2 sine, you get -2 cosines. If you do a 6, you get 0, and you do that guy, you get -2 sines. And then we can get the speed, which is the magnitude of the velocity vector. So this guy squared, the middle guy squared, and the end guy squared, and that will be us. So -2 sine t squared, middle guy, and the end guy, all squared. So we're going to get 4 sine squareds. We're going to get 36, and we're going to get 4 cos squareds. And if you see sine squares and cos squares floating around, isn't there a good chance something's going to combine using a very simple trig identity? What do you get from these two guys? What do they become? Take an answer from anyone. What do you get if you take 4 sine squared plus 4 cos squares?
You get 4, right?
You get 4. Plus, of course, the 36 that you had, which is the square root of 40. And I think Weber sign is kind of generous, and it would accept that. But really, 2 square root of 10 is prettier. Think of 40 as 4 times 10, and that gets you square root of 4, which is 2 root 10. And that's the answer. So let's see if we can get something that requires a bit more work. They were pretty straightforward. I get a chain rule one here. Yeah, let's do this one. The position curve is 8 square root of 2 via t, e to the power of 8t, and well, can you say e to the power of -8t. So if we want to get the velocity vector, you find the first derivative. Ugly number t just gets you ugly number. If you differentiate e to the 8t, you get e to the 8t times 8, and the other one times -8. And there's your velocity vector. If you want to get the acceleration vector, it's the second derivative. Well, if you differentiate a number, you get 0. If you differentiate this guy, you get 8 of these times another 8, which is 64. And if you do this one, you get that guy times another -8, which also gets you 64. And last but not least, we get the speed. So, square root of this guy squared plus this guy squared plus this guy squared. Eight root 2 times another 8 root 2 gets you 2 64s, which is 128. This guy gets you 64, and e to the 8t times itself just basically doubles up the power. and the other one's positive, and you also double up the power. I'm going to bring this guy back. When we did this speed, the three terms that we got in the middle might have been, and most often is, a perfect square. And I just told you that this one wasn't, right? It didn't work. This one is a perfect square. But to be able to see it, I'm going to have to change the order in which the terms are written. Biggest to smallest. So that's big and positive. That's the smallest because it's big and negative. And so that guy is in the middle. This is that expression written down in its order, right? From smallest, from largest power to biggest. And I'm telling you that it is a perfect square. And the rules from Monday are that that guy gets you 8, and doesn't this guy get you half its power? So that's this piece. And this guy gets you 8, and half its power gets me that. Are you comfortable about how the first and the last term make it work, and the middle one, it sorts itself out, right? And squares of square roots play well together. And I'm really happy if you got that. But I'd be even happier if you could take out a common factor of 8. So there's your speed. Now you might say, well, how do I know? There's that damn thing again. How do I know that this one is not a perfect square and this one is? Well, technically, you don't really know until after the event. But if this one was going to be a perfect square, wouldn't it have to be 3t squared plus a square root of 2? And if you FOIL it out and it doesn't work, ain't any good. This one, if you FOIL it out, you get that one, so it does work. And so I guess the easiest, not maybe the easiest, but the only way that you can tell is 3 terms inside a square root going to be a perfect square compared to when there's not, is that you make the perfect square and then you check it by FOILing it out. And does it FOIL out to give you the original? Great. If it FOILs out, for instance, this one, it would have to be 9t squared plus the square root of 2, all squared. Can you trust me, if you FOIL that out, you get 18 root 2t squared in the middle, and it doesn't match that guy? Check it out, but it doesn't work. And that is that guy. Any questions so far about velocity, acceleration, and speed questions? No. Now, none of the ones I've gave you involved product rules or quotient rules or generals, right? I'm not going to go through an entire question. I just want to show you an ugly question where that might be the case. If you got that space curve, wouldn't you have to do the product rule to get this guy's derivative, quotient rule to get this guy's derivative, and wouldn't this basically be a chain rule? Right. You recognize 2 things multiplied as a product rule, essentially a fraction as a quotient rule, and the sign of a multiple, in this case 10t or 10t squared, whatever, would be a chain rule. We don't have any like that. The only question that does look like that is question 5. And I'm not going to do question 5. I'll just give you a heads up on it. You have e to the t cosine t, at least once you FOIL it out, you do. And you've got e to the t sine t. And then you've got 8 e to the t, 8t. Oh, yeah. Let's try that again. E to the t cosine t, e to the t sine t, and 8t, yeah, 8t e to the t. Now that's what you're going to end up with. This is what it looks like in the homework. They're using the I, J, K notation. And you see this e to the t needs to be multiplied to get this guy. These two get distributed to get that guy. And these two get distributed to get that guy. So this is going to be, this guy here is going to be your space curve. Now, to differentiate that, isn't that going to require a product rule, another product rule, and a third product rule? And then the second derivative is going to be even worse looking, right? Because you'll have to differentiate whatever these three end up being. And and when you come to do question 5, it's a perfect square. So as ugly as this thing looks, factor things out, do what you need to do, but it will be a perfect square when you're finished. And that's essentially the first 5 questions covered. Is there anything you want to talk about before we move on to the next group of questions, which is another 4? So if I give you an R of t, a space curve, you're happy about first derivative is velocity, second derivative acceleration, and then the magnitude of this guy here is your velocity, is your speed, I should say. And you might or might not have to do some perfect squares and side square roots when you do speed. Well, the next group of questions, 6 to 9, involve us solving this problem. Suppose I tell you the acceleration vector. Suppose I tell you that the acceleration vector is 6t, 2e to the t, and what else? Sine 2t. And I also tell you what are sometimes called boundary conditions. I tell you that the velocity at time 0 is 1, 0, 0, and that the position at time 0 is 0, 1, 0. Right? And from this information, we're being asked to find what the velocity vector would be and what your space curve would be. Now, we've just been doing things this way, haven't we? We've just started with this guy, differentiated to get this guy, and then essentially differentiate again to get acceleration, right? So if I tell you the acceleration vector is 6t, 2e to the t, and sine 2t, and I ask you to figure out what the velocity vector is, what do you think you need to do?
Integrate it.
You need to integrate. Agreed. Opposite of differentiate. So to get the velocity vector, won't I have to integrate 6t, integrate 2e to the t, and lastly, integrate the sine 2t. So that makes sense. If you work backwards, shouldn't you integrate? If you work forwards, you differentiate, right? Two-way street. Now, there is a little hiccup that we have to deal with, and I'm about to show you it right now. If you integrate 6t, you add 1 to the power and then divide by the new power. And then you should have plus an arbitrary constant, which I'm going to call C1. If you integrate 2e to the t, you will still get 2e to the t plus an arbitrary constant, which I'm now going to call C2. And when you integrate a sine, you get a negative cosine, 2t. Oh, and you divide by the new, so it's negative a half, plus an arbitrary constant, which I'm going to call C3. Now, each one of these arbitrary constants is different, right? That one could be 0, that could be 2, and that could be a million. And to indicate that they're different, that's why I have C1, C2, C3, right? 3 separate integrals, 3 different, probably, arbitrary constants. And now we bring in this piece of information, the boundary condition that says the velocity at time 0, which in this case would be 3 lots of nothing squared plus C1, which is just C1, 2e to the nothing, which is 2 plus C2, and negative a half, the cosine of nothing, which is negative a half, because cosine of nothing is 1, plus C3. And that is going to equal, because we were told it was equal to 100. So we are using the boundary condition that the velocity at time 0 is this vector, plugging in 0 in our generally solution to come up with this relationship. Do you see how this is going to allow us to find out what numbers C1, C2, and C3 are going to be equal to? How am I going to do it? How am I going to find, say, C1 then?
Plug in whatever numbers work to create the IJK desires.
Right. The X component, the I's, tell me that C1 has to be 1. If we do the second one, that guy has to be 0, which means C2 has to be what? Negative 2. We know that C1 has to be 1. And then lastly, we have negative a half plus C3 has to be 0. So that makes C3 1/2. Which, when we put that together with the velocity vector, we now have its exact solution. It's 3t squared plus 1. Then it's going to be 2e to the t, take away 2. And then it's going to be this guy here, negative 1/2 cosine 2t plus a half. That makes sense? Integrate to get the velocity vector, but the velocity vector is going to have 3 arbitrary constants. Use the boundary condition to find out what the values of C1, C2, and C3 are. Once you know them, plug them in here, here, and here, and now we know everything. We know the velocity vector in its entirety. So how are we going to get the position vector, the space curve? How are we going to get it?
Integrate again.
I hear you. So the integral of this guy, the integral of this guy, and the integral of this guy. So the position, the space curve vector is add 1 to the power, divide by the new power gets me t cubed, integrate 1, you get t, plus an arbitrary constant, which I'll call C1 again. This guy here gets you 2e to the t, take away 2t, because that's integral of -2, plus an arbitrary constant. Cosine gets you a sine, another half, so you're going to get -1/4 of the sine of 2t, plus a half t, plus a C3, bit crushed at the end. And now we're going to use this guy to figure out who C1, C2, and C3 are. So I know the position at 0 is 0 cubed plus 0, that's C1. 2 lots of 0, which is 2, take away nothing plus C2. And -1/4 times this guy is nothing. This guy is nothing, so you just get C3. And that's going to be the vector 0, 1, 0, because we're using this guy now. And if we match the x's with the x, C1 will be 0. If we match the y components, we get that 2 plus C2 is 1, which means C2 is -1. This one basically tells us what we already know. And lastly, we get C3 has to be 0, which is pretty obvious. Now you put those guys in here, here, and here, you have got your complete version of your guy. It's going to be t cubed plus t plus nothing. Middle one, 2e to the t, take away 2t minus 1. And the guy at the end, -1/4, the sine of 2t, plus a half t, plus nothing. So we'll write it down. And we now have our position vector. So the first part of today was differentiate and then differentiate again. And this part seems to be integrate and then integrate again. And we have an added extra piece of work that when you integrate, it's helpful if you can find out what C1 and C2 and C3 are, which is what these guys here are for. Any questions about that one? Are we good? You want to say another one?
So, how do you know when we're trying to find the C's? Because I notice sometimes we don't find it and sometimes we do.
If you are being, well, let me show you the questions so I can show you what they look like. And that way it's a little bit easier, I think, for me to explain why I know we have this extra step, right, where we have to find all the C's, the arbitrary constants. You'll know that that's the case when they tell you boundary conditions. Let me try that again. I don't think I'm on the right page. Right, it's a bit bigger. So we take an example, question 5. Right. Maybe back. Here we are, question 6. Can you see that they give you the acceleration function? It's an IJK notation, which is essentially one I just did. And there's your two boundary conditions. So when they give you boundary conditions, you know you're going to find C1, C2, and C3. Right. If we look at this question, can you see that the vector would be 19t, comma e to the t, comma e to the -t. And this would be v of 0 equals 0, 0, 1. and r of 0 would be 0, 1, comma 1. And so I know, because you are telling me velocity and position at a given time, that you're giving me a boundary condition, which means I will need to find out what numbers C1, C2, and C3 are. If this bit was missing, right, if that wasn't there, and they just said, here is A of t, find out R of t, then you would just have C1, C2s, and C3s. That would be them, right? That's what you would have. You wouldn't find what numbers there were, because there isn't any information that would allow me to do it. So
okay, you would put C's in your answer in that case.
yes, so you took plus C1 plus C2 plus C3. And
Okay.
hopefully you wouldn't have to do another integration, because wouldn't C1 become C1t and C2 would
yeah, it'd be a mess. Yeah.
it would get really ugly really quickly.
Okay,
Question
cool. Appreciate it.
Okay, question 8 looks like pretty straightforward, I would say. And that's the last one in this group, right? Just question 9. I think we should do one more. You agree? Just to see it. No, it's a little bit long to do these questions, but as I'm scanning through these, with the exception of 6, which is one I just did, 7, 8, or 9. Any particular one you want me to try, just for more practice, so you're comfortable with the method? I'll pick one, but if you can see one you'd prefer, that would be better. 7, 8, or 9.
Do 9.
9.
Yeah.
9. Okay, 9 got the job. Give me a few seconds to set it up. You know that WebAssign likes I, J, and K half the time, and I don't. So I turn all my questions into vector notation, right? I just think it easier if you do one technique, no matter what the question is. So if you're wondering what I'm doing here, I'm just converting it into the way I prefer things to look. It's just a
So,
Mhm.
so when in doubt, just do ij. So just turn ij and k into a vector function.
I would. It's easy for me to lose digits. If you tell me v of 0 is I, it's sometimes hard for me to know that means 1, 0, 0. I forget which place it goes. Or if there's a missing j term, sometimes I don't notice it. And, you know, I found it helpful, but not everyone does. So if you're comfortable with I, J, and K's, go ahead. There is no problem. That's what the question looks like if you do it in vector format. The boundary conditions, I think they picked 0 because it's an easy one to calculate, but couldn't the boundary couldn't it be v of 1 equals or v of 42 equals, right? There's no reason it needs to be v of 0. But anyway, v of 0 is 1, 0, 0. That was basically I on its own. And the position at 0 is no i's, 6 j's, and negative 2k's. So there is your information. We are going to find the velocity and the position vector of using this guy. So velocity vector is the integral of the acceleration vector. So it's going to be the integral of 2, the integral of 6t, and then finally the integral of 12t squared. That guy gets you 2t plus an arbitrary constant. Add 1 to the power, divide by the new power. So 3t squared plus an arbitrary constant. Add 1 to the power, divide by the new power, and that gets me my third arbitrary constant. Are we good? So that would be the general version of the velocity. But since I know this boundary condition, I should be able to find out what numbers C1 and C2 and C3 have to be. Well, the velocity at 0 is 2 lots of 0 plus C1, 3 lots of 0 plus C2, and 4 lots of 0 plus C3. Well, you couldn't get much easier than that, right? C1, C2, and C3. And it equals 1, 0, 0. Now, if you're really lucky, you'll get a question that matches like that. Would you agree C1 is 1 and the other two are zeros? Right? C1 is 1 and the other two are zeros. So I could just cut to the chase and write the answer down there. It's 2t plus 1, 3t squared plus nothing, and 4t cubed plus nothing. There is your perfect everything you need to know about velocity vector. Are we good? Right, same process. Integrate now to get the position vector. The position vector is the integral of the velocity vector, which is going to be the integral of 2t plus 1, then the integral of 3t squared, and finishing with the integral of 4t cubed. You integrate that guy, you get t squared plus t plus an arbitrary constant. The next one, power rule plus an arbitrary constant. Next one, well, that's really nice. Power rule plus an arbitrary constant. And then we'll use this guy to figure out who C1, C2, and C3 are. And the position at 0, nothing squared plus nothing plus C1, nothing cubed plus nothing, nothing to the 4 plus nothing. And that's going to be 0, 6, negative 2. And again, we got really lucky here. C1 will be 0, C2 will be 6, and C3 will be negative 2. Put that information into R of t, and we have t squared plus t plus nothing, t cubed plus C2, which is 6, and t to the 4 plus C3, which is negative 2. And there is your position function in all its glory. Do you feel this one is going a lot smoother than Monday? It has a nicer flow to it, doesn't it? It has less weird stuff happening.
It seems more streamlined.
That'll do. They're still, you know, they're not as long as Mondays, but they're, you know, especially when you have a lot of, you know, pieces to do, they'll still take you a fair amount of time. Right, so there are only 2 more topics and we'll be finished today, which is fine. How do you find the time when a speed is minimal? What on earth does that look like? Well, let's give you the only question we've got, which is question 10. At least I'm doing a version of it. Yours will be different. You're given a position function. So can you imagine that this is a space curve, and it's doing its thing in 3D space. And at some point, your speed, not your velocity, right? You're going 80 miles an hour downwards, or you're going 20 miles an hour east, right? Your speed will change as you travel along this curve, right? But someplace, hopefully one place, the speed is going to be at a minimum, right? The slowest speed possible, or it's going to be a maximum, right? So you were watching, or if you were traveling along this curve and it was like the roller coaster had the speedometer on it, so you could tell what speed you were going at any instant at time, and you took a little video on it with a little timer at the bottom. Wouldn't it be some part of the journey where you were going really, really fast, faster than any other part of the journey? And then there might be another part of the journey where you're going slower than anywhere else. So that's what this question is about. Finding the time, finding the value of t when the speed is fastest and or slowest. In this one, they want the minimum. So we're trying to find when is it slowest. And the answer is going to be t equals 10 seconds or t equals 2.1 seconds or something similar, right? So let's see how we're going to tackle that problem. Let's just rewrite the original. And I'm going to find the velocity, which is this guy's derivative. Are we comfortable about the velocity being the derivative? Nothing too special. Now let's get the speed. And the speed is going to be the square root of this guy. That fella, that fella. Oops. That guy. So it's going to be the square root of 4t squared, 49. If you multiply this out, you'll get eventually 4t squared. Oh God, 32, 64 minus 64t, 16 16s, 256, which I'm now going to try and tidy up. Those two get me 8t squared, negative 64t, and if you add this guy and this guy, that's 290, 305. So our question becomes, what's the smallest value of speed, right? That's our problem. For what value of t will this be the smallest? Now you might say, well, t equals 0 gives me the square root of 305. Maybe that's it. Maybe there's a value of t where all of this becomes 0, in which case speed is 0. Maybe there's somewhere between those two extremes, right? You know, 10 seconds, where we can get an answer that's, you know, that's the smallest. And we're trying to find this, and I'm going to put it in Desmos as a backup, but we are trying to find the speed minimum here.
So
And,
don't you want the t that makes that the square root of 0?
we would love that to be true, but we might not be able to get 0. Can you imagine that this is the x-axis and it might be, you know, not 0, but it's minimum, right? The bottom of a smiley face. So we have to figure out, how do we find the value of t where this function is a minimum? How do you think we're going to go about that? Okay, in Calc 1, how did you find the minimum value of a function? What did you do in Calc 1 to find the minimum value of a function?
I'm just kind of guessing here, but find its limit to infinity.
Oh, that's interesting. It's not, I think I know where you're coming from. No, it's not that. That would be essentially what's the limit. That might or might not be the minimum, but it's not in general true that that's where you get it. Okay.
Isn't it where the tangent line is just constant? Like it's at a maximum or a minimum? So the
Yeah,
slope is
okay.
0?
If this was the curve, right? Imagine I put that into Desmos, which I will do later, and it's a curve. Let's say it's a curve looks like that. What do you notice about the tangent line here? What number is that tangent line?
It's a constant.
Yeah, what number? You write it as a constant. What is the slope of a horizontal line?
There's no slope.
0. So to solve this problem, for what value of t is this function going to be at its minimum? We are going to find when the derivative is 0. So we're not going to find out when the guy inside here is 0. We're going to find out when the derivative of this thing is 0. It's not quite the same thing. So let's call it f of t. And it's the square root of 8t squared, take away 64t, plus 305. And since I'm going to be differentiating this function and then trying to find out when it's 0, I'm going to call it 8t squared, take away 64t, plus 305 to power a half. And now I'm going to differentiate it. And it's a chain rule. This is called the inside function. So it's going to be 1/2, this is a power rule, the inside function to the power of, well, take 1 away from that, negative 1/2, times the derivative of the inside function, which is 16t take away 64, which is now going to look something like this. 1/2 times this guy gets me 8t take away 32. This guy is going to go on the bottom. And that's the derivative. And so we are trying to find out when is the derivative 0. So we're trying to solve when is this guy 0. Great. Now, in algebra, if you want to find out when a fraction is 0, the bottom doesn't matter. What does matter, however, is that the top has to be 0. Right, 0 over 42 is still 0, right? The bottom doesn't make anything 0. And you might say, well, what about 0 on the bottom? Well, 42 over 0 isn't 0. 42 over 0 is an undefined value, which is not much use to us. So all we do when we have a fraction equal to 0 is find out what makes the top 0, which in this case is 4 seconds. And we have answered our question. When is the derivative 0? It's 0 at t equals 4. That's what they wanted to know. Now, if you want to know what is that minimum speed, they don't actually ask it, but if they did, it would be the square root of 8t squared, take away 64 times 4, plus 305. And whatever that horrible mess is, which I do not know what it is, but can we pretend it's 42, then that would be the slowest speed that you'd ever go on that roller coaster. Right? So as you're traveling along that roller coaster, you might go pretty fast, but you'll never go slower than 42. And that's what we've just found out. Right? The time it takes to do the minimum. Now, I said I was going to show you that on Desmos, or I should actually have said GeoBra, but that's fine. Let's see if I can make that happen. Gonna have to wait a few seconds while I load up about 4 windows and get myself thoroughly confused. And GeoBra. Okay, I think I'm ready. My usual too many windows open. Right, here's our guy. Now, actually, I'm saying that I take that back. This is a scalar function, so I can use Desmos. Easier to see it as well. So I'm going to put in my function. It's y equals, and it's square root of, and it was 8t squared, take away 64t plus 305. And for some reason, I've picked up some brackets that I don't remember typing. There we go. Now, can you see the curve, which represents the speed at any given point in time? And would you agree there is the slowest speed? And it happened at 4 seconds. And now I know what that weird number is. So when I said, oh, let's pretend it's 42, it's actually the slowest speed it gets to is about 13.3 miles an hour. So as in Desmos verified that I found the right place, t equals 4.
Well, that's definitely not a roller coaster.
Oh,
that
come on. You could build a roller coaster that you just went down one hill and shoot up the other. Come on, use your imagination here. It probably wouldn't be a very exciting roller coaster because technically,
But at the bottom, wouldn't you be going the fastest, technically?
evidently you would think so, but not in this space curve. So can you imagine sliding down this very steep hill and there was rockets trying to push you up the way? Could you be actually going pretty slow at the bottom?
Definitely.
Be a weird roller coaster.
Is that because that you lost all of your speed and or is it inertia trying to go back up?
I don't know. This space curve tells you where you are at any given time. And so according to this particular one, when you get closer to the bottom of the hill, you're actually going slower, which is kind of, let's not do roller coasters anymore. You are a rocket zooming down and then changing direction. You're a jet engine zooming down and then looping the looping going back up. But evidently you're a jet engine that's firing its retro rockets to slow itself down. So this shape, the smallest speed actually happens right there. Now, this is actually a function representing the speed. If I put in the roller coaster shape, which is the original function, which looks something like this, we actually might see what the roller coaster looked like. Oh, what are you doing? Geobra keeps trying to make me do, it thinks it knows better than me. Sometimes it does, but not this time. It's doing some weird bracket up the top. Go away. Okay, do y equals y just to get rid of it there. There we go. Let's try this again. T squared, comma 7t, comma. Right. So this is the original space curve, which is actually what the roller coaster looks like. Can I get rid of this guy? Yes. Okay. What a boat. Well, it has a bit of a curvature to it. It doesn't actually look that different in the velocity curve. You see it just comes down and goes up. Okay. Didn't get anything useful out of that. I was hoping to see something a little bit more. Sometimes you have to trust the math. And if the math says t equals 4 is the slowest, then it is t equals 4. Because objects don't always work on gravity. Don't they also have jet engines that fire against or with gravity, right? They could change accordingly, which is only one of that type, which brings us now to the end of this group of questions. And what we're, oops, that was a weird noise. Okay, hold on a second. There we go. What we're left with now is our last two questions, essentially. And these are how to find the tangent, what are called the tangential and normal components of acceleration. So we'll try and explain what these guys are. There's your space curve doing its thing. If you choose some point, let's call it T. Right. The unit tangent vector, which I'm calling T here, right? Doesn't he go in the same direction as the velocity vector, but he's just 1 unit long? And then you have a second vector, which is the unit normal vector. Which I'm trying to draw. I think the unit normal vector goes this way. And it's at right angles to it. Centripetal force vector, which is, that's the direction it goes, and it's 1 unit long. Now, the acceleration vector, which we know as the second derivative, right? The acceleration vector is actually made up, oops, of a linear combination of the unit tangent vector and the unit normal vector, which according to the math of things is, do you see these two vectors make a little plane? You know, if you imagine two vectors, there'd be a plane that you could form using those two vectors. The acceleration vector, which might be this red guy here, is always going to be in the tangent normal plane. And these two numbers here are called the tangential component and the normal component of acceleration. And evidently, people who are interested in objects moving in 3D space, these two numbers are quite useful. I have no idea why they want to know it, but they want to know it. And if they want to know it, we'll find it for them. And if you look at the formulas for calculating the tangential component AT, and the one underneath it, which is the normal component, they're pretty ugly. To get the tangential, oh, by the way, these are scalars, these are numbers, or at least there'll be expressions with T in them, but they'll be considered scalar. The dot product of the first and second derivative divided by the magnitude of the first derivative. And then the normal component is the cross product of these two guys divided by the magnitude of the first derivative cubed. So all you need to do is remember the formula and then apply it. So there are two questions. This is probably going to be the messiest part of today. And we are going to find these two guys in each case. So here goes.
That's very similar to how you do the normal and tangential for the position vector. Just now you're applying for acceleration.
Yes, yeah, it's a horrible formula, but it's that convoluted bits and pieces that we did, yeah. So let's look at this fella here, right? So to get the unit tangent vector, I need to know the first and second derivatives, right? In fact, to get this one, I also need the first and second derivatives. So my first stage would be, and I'm rewriting these guys, like this. Right, that's the way I'm going to rewrite this guy. He was originally in IJK notation, but I've converted it into the usual version. Now the first derivative is power rho, which gets me that. Power rho, which gets me that. And then the second derivative, oh, this one's going to be a lot nicer than I thought. Nothing minus 30t, 30, and 0. Okay. Now, to get this fella, find the dot product. First derivative, dot product with the second derivative. So it's going to be this guy times this guy. So it's going to be 15t take away 15t squared times negative 30t plus this guy times this guy, which is 30t times 30 plus a whole load of nothings. And that gets me, oh yeah, negative 450t plus 450t squared plus 900t plus nothing. And that gets me 450t squared plus 450 t's. So the dot product of the first and second derivative is that quadratic. Are we good? So far, so good. Any questions before I move on with this question? Okay. The second component I need to know is this magnitude. Well, the magnitude of the first derivative is the square root of this guy squared plus this guy squared. And this guy is going to get me 225. This guy times this guy is going to get me minus 450 t squared. This guy squared is going to get me plus 225, yikes, t to the 4 plus 900 t squared. Put this guy first, 225 t to the 4th. These two get me plus 450 t squared. We're going to finish with 225. So far, so good. Taking a look at this question, actually, I'm taking a look at the answer to this question. It should be here. This, according to them, is a perfect square. Wow. That was very clever. I wouldn't, well, I should have guessed. Isn't it get 3 things inside a square root? And 3 things inside the square root have a very, very good chance of being a perfect square, right? Great. Right, so square root of this guy is 15, square root of this guy is half its power. Square root of this guy is 15. Check it out, but if you FOIL that, you get the original. It is a perfect square. Which means that this fella is now 15t squared plus 15 because the square and the square root cancel each other out. I guess that's why these guys get picked, get paid the big bucks. Do you know how hard it must be to create a question where this happens? I mean, it'd be very easy to make it so it doesn't harm. Well, let's put the whole package together then. If you want the tangential component, it's the dot product of the first and second derivative divided by the magnitude of the first derivative. And this guy on the top is 450 t squared plus 450 t, and the guy on the bottom was 15 t squared. Check that out. Plus 15. Okay. Is that 450t still there? Let me check. Is there any tidying up I can do on this thing? I can see a little.
Could
Anybody see?
reduce that 450t squared and that 15t squared.
Okay. And I bet you that goes into that. How many times? I don't know. 30 would get me 9. So is that 60? No, it wouldn't be 60. Somebody, 450 divided by 15. I'm pretty sure it's a nice number. Anybody got it?
30.
Agreed. Yeah, pretty reasonably nice. I wouldn't say it's perfect, but it's pretty good. I kind of like that. That was nice. Now, the normal component needs to know the cross product of these two guys divided by the magnitude cubed. Well, I already know this guy, right? So the only thing I need to find is the cross product of the first and second derivatives. So they're going to be an I, they're going to be a J, and they're going to be a K. And I want some nice stuff to happen here. So the first derivative is 15 take away 15t squared. The middle term is 30t and the last one's 0. That one's a 0. This is negative 30t and this is 30, right? So there's r dash, there's r double dashed. Our answer is going to be so many i's, subtract so many j's, plus so many k's. So if we cover up this one, okay, I like that. Would you agree? 0 take away 0. Not much happening there. If you go the middle one, 0 take away 0. If you go the end one, you're going to have 30 lots of 15 take away 15t squared, subtract negative, so let's add 30t times 30t. So it looks like our answer has got a 0 and then another 0 and this horrible mess, which is what? 450 take away 450t squared plus 900 t squareds, which gets you 0, 0, 450 plus 450 t squareds. Now the formula is not the cross product, but the magnitude of the cross product. So I now need to find the magnitude of this vector. But instead of doing it the typical square root of this squared plus this squared plus that squared, can't I simply just tell you that it's this fella? How can I do that without any calculation? Why do I know that the magnitude of a vector 0, 0, somebody is just a somebody? Isn't that just the distance on the z-axis? And so that would be its line. That's the reason. So if you don't like that shortcut, square root that squared, and that's what you will get. Now you put the whole package together. and you get the magnitude of the cross product of the first and second derivative, which you've just found, is 450 plus 450 t squared, divided by the magnitude of the r dashed vector, which we got earlier, 15 t squared plus 15. Good. And can anybody see some simplification of this? Okay, give you a clue. I'm going to pull out a common factor 450 from the top guy. You see this 15t squared plus 15? If I pull that out as a common factor and then cube each piece separately, wouldn't I have 15 that guy plus that guy? And you can cancel one of them. That would leave me that guy in the bottom. And 450. God, what's 15 to 450? 30. What's 15 to 32? So you will get 2/15. At least that's the best I can do in my head. So the answer ends up being 2/15, 1 plus t squared squared. Could have been a lot worse. And that is how you find the normal and tangential components of acceleration. It's essentially just follow the instructions and try and do the best you can to make it look pretty algebraically. Right, so factor everything in sight, cancel, collect like terms, all the usual processes. Make it a perfect square inside the square root if you can, that type of thing. How are we doing? We're doing good. Messy but doable.
Definitely.
Okay. You want to see one last one, or should we call it quits? Any preference? Okay. Do one last one then. This is a version of the last question. It's a t squared, and a 6t. I think this one's going to come out a little bit cleaner. And the reason I'm saying that is it looks like these are quite nice polynomials, right? So they should differentiate relatively nicely. The first derivative, well, if you differentiate, that's a t. I know it looks like a 6, but it's a t. You get 1, 2t, and a 6. And if you do the second derivative, you get a 0, a 2, and a 0. But you agree that's probably going to come out really nice. Lots of zeros are good news. So let's go for this fella here first. The only other component that I need is I need the magnitude of this vector. So it's going to be the square root of 1 squared, 2t squared, and 6 squared. And this guy is 36, and 1 makes 37. And this guy is 4t squared. And no, you cannot do any simplification. That's ugly, but that's as good as it's going to be. So if you want to get the tangential, it's the dot product of these two guys, which I guess I should now do, shouldn't I? So the first guy, dot product with the second guy. That should come later. 1 times 0, 2t times 2, and 6 times 0, which is just 12t. Right, now we can put in the pieces. It's the dot product of the magnitude. And 12t goes in the top, and an ugly square root of 37 plus 4t squared goes in the bottom. And it's done. I don't think there are any style points there, right? You can't do anything, collect like terms or anything. Pretty much you can't do anything to that one. That's the final answer. Now the other one, I need to know the cross product of the first and second. So I have an I, a j, and a k. And the first derivative is a 1, a 2t, and a 6. And the next one is a 0, a 2, and a 0. If you're doing cross products, have you noticed that if there's a lot of zeros around, you tend to get a lot of zeros in your answers, right? So I'm pretty sure that's what's going to happen here. So the cross product of the first and second derivatives is so many i's, take away so many j's, plus so many k's. If you cover up the i's, you get nothing, take away 12. If you do the middle one, you get nothing, take away nothing. And if you do the end one, you get 2, take away nothing. And so in this case, you get -12, 0, and 2. And now we need to find the magnitude of it. And the magnitude, when it's numbers at least, is a lot easier. It's that guy squared plus that guy squared plus that's 144, and 4 is 148. And now we can put them together. It's the magnitude of the cross product divided by the magnitude of the first derivative cubed. So it's the square root of 148 over, I've lost the damn thing. Magnitude of a, oh, here it is, that guy. And there's really not an awful lot you can do to that answer to make it look pretty. I'm just saying what WebAssign did to it, if anything. Check it out. Well, evidently the top guy can be written down as 2 times the square root of 37. And I think we're finished. And that cube, I take that cube out. That cube's not necessary. I don't know where it came from. It's there. That's much nicer. So when you're doing the normal component, don't cube the bottom.